Alright, so yesterday afternoon, since it's like just past midnight right now, yesterday afternoon I realized a even more accurate approximation to finding the perimeter of an ellipse based on understanding how calculus works. One of the most fundamental things that wasn't required for this was to throw away the idea that d dx is an operator. It's not. If we actually take apart Leibniz notation and look at what's going on there, all of the pieces mean something algebraically. So you can take it apart and you can figure out what all of the pieces mean. And you can then construct a sense of why the shape constants, the shape coefficients for basically the power rule, why it's 1 over the number of dimensions that you're at, or the inverse of that, depending on which direction we're going. Including, at the 0th term is 1 over 0. Because when we multiply, we're going to multiply by the inverse of that if we're taking the derivative of, say, like a constant. We're going to multiply by the inverse of 1 on 0, which is then 0. So the slope of that constant is 0. But now you hit a dead end going in this direction. But the fractions, they continue going, so like the -1 term is 1 over -1. The -2 term is 1 over -2. The -3 term is 1 over -3. From 1 over -1, you can actually build back up via integration. You can build back up into the positives. But what's going to happen is you're going to have to take logarithm of 1 over your dimension, basically, right? In order to get the dimension, the original dimension specification, it's going to be the logarithm of 1 on, or it's going to be the logarithm of the dimension, which is the integral of 1 on the dimension, right? So like 1 over x, its integral is ln x, right? So what we want to do, if we're looking for the perimeter of an ellipse, which operates as in the second order, is we're going to have to take a triple integral of the inverse of the reduced eccentricity, where the reduced eccentricity is assuming that your semi-major axis is 1. So it's really just in terms of b. So now everything is completely in terms of one variable, and we can then build up in a principled way what everything looks like. And what this yields is a very, very accurate approximation of the perimeter of an ellipse. So this is what this equation looks like. See, I'll copy this in here. So this is the commented part, right? So the logarithmic approximation is from taking the triple integral of the inverse of eccentricity, and that's specifically reduced eccentricity, m, right? So your perimeter constant is approximately 4 times the quantity, 1 minus the quantity pi on 2 minus 1 closed quantity on 3 times the triple integral of 1 on your reduced eccentricity dm cubed. And then your perimeter will just be that times the half, right, of a real parabola, or a real ellipse. Right, and this was developed this afternoon. So here I'll run it, and say let's choose something like a quarter. So that'll give you this runs program basically that I wrote in November. I just added this in today. So here your error for the binomial GIC approximation is just under 2% compared to the Ramanujan approximation, which is pretty accurate. Today's new logarithmic approximation is, what is that, about 12 times more accurate? 12 times closer to Ramanujan's approximation? About. Six times. It's too late in the day. I can't do math. Yeah, quite a few. It's notably more accurate. And it maintains this. Here, this one is actually, binomial GIC is closer to Ramanujan's than the logarithmic approximation, but both of them are. They're all really close to each other. And honestly, I don't know which is more accurate, all told. My guess is this, but I honestly don't know. So yeah, there's just a little demonstration. Link to this will be in comments. Link to the code for this. But yeah, just a little demonstration of what you can do with a principled understanding of how things work. Ignoring bullshit canonical claims of things that don't make sense. Like, oh, ddx is an operator. No, it isn't. It's a vector that you're multiplying by, which is why it comes apart. When you introduce d dx on the one side where it's just y, you get dy dx, because it's a vector quantity that you're multiplying by. And when you're taking an integral, the dy part disappears and the dx comes into the numerator because you're multiplying by it instead of dividing by it. When you're taking the derivative, you're dividing by dx. When you're taking the integral, you multiply by dx because it's a fucking vector that you're multiplying by. It's not an operator. I don't understand how anybody could get to calculus and have such a fundamental misunderstanding of absolutely everything they're seeing. It's not that complicated. It's right there in the notation. How are you fucking this up?